All right, a little piece of 5.4 and 5.5 here. So the only thing remaining was I hadn't gone over how to do absolute values. Okay, so first step, rewrite this. The absolute value, remember, it makes everything that is negative positive. So I have to compensate for that. So we're gonna rewrite this as two different integrals. This is now gonna be 2x minus 1 and another 2x minus 1, but one of these is gonna be negative. And then also, because I have two integrals now, I will have two integrals anyway, my limits aren't going to work. I actually need to figure out where I need my integral, the negative part of the equation and the positive part. So to do that, you take 2x minus 1, set it equal to 0, and figure out what x is. So x is 1/2. So this is my partition. This is where I'm going to chop up my my limits. Okay, so this is now from 0 to 1/2. Something goes here. And I'm going to add it to from 1/2 to 2. And then, well, something goes here, dx. Now the question is, what goes where? And the problem is, absolute value makes anything that is negative, it makes it positive. If you take a brief look at what the graph of an absolute value looks like. Now this is not totally 100% accurate, but we do know that it's going to look like this somewhat, right? 2x minus 1. The graph of this line is just a straight line. And it's a straight line that looks like this. What absolute value does is it takes this piece right here, which is negative, and it makes it come up here. And that's how we end up with that half part of the v. Okay, so if you look at the graph, the left side is the part that needs to become positive. So the left side is the side that would normally be negative, right? So we're trying to do the job of the absolute value without actually having the absolute value. So if the left side is the part that's negative, well, let's see, how can I make something negative positive? Oh yeah, I can just tack on a pretty little negative. If I have a negative there, it'll make my answer positive if it's already negative. And this part, the left part, is the part that would end up being negative. So with my negative there, it makes it positive. So from 0 to 1/2. And I said that my graph wasn't completely accurate. But from 0 to 1/2, that's where I need to be like, okay, so this is supposed to be negative. So I'm going to put a negative to make it positive. And then the other piece is just going to be the positive version. All right, so integrate. And this right here is just leave that alone. Okay, so oh, I'm just integrating, aren't I? So I get x squared divided by 2, and there's already a 2 there, so x squared minus x. So 0, 1/2 plus. Same thing, x squared minus x from 2 to 1/2. And, oh yeah, let me make sure I don't forget my negative. There it is. Okay, so now we're going to evaluate. So plug in the 1/2, and I get 1/4 minus 1/2. I'll plug in the 0, and it's 0, so I don't have to do anything with that. Plus, and then plug in the 2, so I get 4 minus 2, and then minus, plug in the 1/2, I get 1/4 minus 1/2. And that should look familiar because it's the same as over here. So this is 0.25 minus 0.5, basically. So I end up with negative 0.5. And then plus, and then so over here I have 4 minus 2 is 2. And then minus negative 0.5, so a minus a negative is positive. And I didn't mention it before, but this negative out here and this negative do become positive, right? So I have 0.5 plus 2 plus 0.5. Um, so unless I did my math wrong. Oh, I did do my math wrong. Ha ha ha. 0.25 minus 0.5 is 0.25. Wait, 0.25. Let's just 0.25. All right, my bad. So 0.25 plus 2 plus 0.25 is 3.5. Okay, and that's that. No graph required. I mean, I graphed it kind of to explain to you why part of this had to be negative. That's about it. Next. Okay, so this time the whole equation is not in the absolute value, just the x. So, set this equal to 0, right? So x equals 0. So that's where my partition is going to be now. So I'm going to have one from -4 to 0, right? Dx plus from 0 to 4, and then something goes there, dx. Okay, so using the same logic as before, I'm going to have to rewrite this. And so it's currently 4 minus x. Now this graph of the absolute value, since the minus is in front of the x, it's actually facing down like this. And the line 4 minus x is actually this. So what I need is something that is like this, right? I need this to come down here. So the left side from 0 to, or from -4 to 0, or from 0 to -4, whatever. That's the side that I'm going to have to change. And in order for it to look like the blue line, I need 4 minus -x. Okay, just like before. In the previous example, I just took what I had and put a minus in front of whatever was in the absolute value. I'm doing the same thing here, only that 4 minus x is 4 plus x. Which makes sense, because 4 plus x would be my blue line. That's a positive slope line there. Okay, so I'm looking at the graph. The left side is the side that I need to be 4 plus x. And then the right side is going to stay as is. I hope you're seeing a pattern here. Okay, so integrate. So I get 4x plus x squared divided by 2 from 0 to, well, from -4 to 0. And then, so 4x minus, I just want to make sure we see that there is a minus. 4x minus x squared divided by 2, and that's integrated, or evaluated from 0 to 4. Okay, so do math. So plug in the 0, I get 0, minus, and then plug in the -4. So -16, and then 16, or -4 squared is 16 divided by 2, that's 8. And I'll do the other side. Plug in the 4, I get 16 minus 16 divided by 2 is 8, minus 0. Okay, so 16 plus 8 is -8, but that negative in the front here makes these be positive, right? So 8 plus, and 16 minus 8 is also 8. So I'll have 8 plus 8, so my answer is 16. Okay, next, area of a trapezoid. So 4 or 5.5 is trapezoidal rule. Trapezoidal rule is just basically the same thing as LRAM, RRAM, just that instead of using rectangles, we're using trapezoids because trapezoids can fill in the area a lot better. If you look at all these here, okay, well, first of all, here's my version of a little trapezoid, okay? And the formula for area of a trapezoid is you take the height, which is this right here, and you add up the bases. So this is a base, and then this is another base. Base 1 and base 2, it doesn't matter. You add them up, you multiply by the height, and then you cut that in half. And that's the area of a trapezoid. Okay, so trapezoids normally look like that, or you're probably used to these versions of them. But it's still the same idea. This is the height right here, and this is the base, and this is the other base. 1 and 2, 2 and 1, doesn't matter. All right, for the purposes of this, of graphs, we're going to use this trapezoid, but standing up. So this right here is still the height, but it's actually, how wide our interval is. And this is still base 1, and this is still base 2, or vice versa, it doesn't matter. But how tall this is, right? These are our y values. Kind of like the left point and the right point, the right end point. And if you see how I stacked all of these up, they are more conducive to find the area underneath the graph. Because imagine a curve like this, right? There's a lot less space left over there than if we were doing LRAM or RAM. Okay, oh, one more piece of information. I do need you to write this down. Trapezoid, and I just refer to it as trap sometimes. The trapezoidal approximation is actually equivalent to the left rectangular approximation method added to the right. So LRAM plus RAM divided by 2. If you take LRAM and RM, add them, divide by 2, you get the trapezoidal approximation. Okay, so use 4 trapezoids to approximate the area under the curve from 1 to 3. So here's 1, 2, 3. So from here to here, and they want me to use 4. So I'm going to have 4 trapezoids. So it'll be something like this. And then, and then, and then, Okay. Now, I'm going to use a chart. I'm going to plug in, let's see, I'm going to plug in 1, 1.5, 2, 2.5, and 3. Right, because those are the numbers 1, 1.5 right here, 2, 2.5, and 3. Right, when I plug those into my equation, I get 1, 1.25, 2, 3.25, and 5. Alright, so just imagine this. I'm finding each and every individual area. Now, the height of my trapezoid, and I want to refresh you, area is 1/2 times h times b1 plus b2. Now my height, for all of these are the same, right? It's going to be this width, 0.5. And so I'm going to multiply that by every single base added plus the other base, right? The bases that I add, and I'm going to multiply by 0.5, and then multiply again by 1/2 or 0.5, whatever. So just like when we did LRAM and RRAM, I can go ahead and put the 1/2 on the outside because all of these numbers are going to be multiplied by it. And then I can multiply the 0.5. I'll just leave it as a decimal just so that we know the difference. So this is the H part, right? And then I'm going to multiply by B1 plus B2, but I don't have just one of them. I've got here 1 rectangle, or trapezoid, 2 trapezoids, 3 trapezoids, 4 trapezoids. So this is really going to be 4 different things I'm adding. So here, and then here, and then here, and then here. Right? So base 1 plus base 2. Alright, so follow along here, folks. Let me do another color. So base 1 here, that's 1. Base 2 for this trapezoid is 1.25. So 1 plus 1.25 is 2.25. And then you're going to keep going for the next one. For this trapezoid, I'm using this base, which happens to be the base of the previous one, right? Plus this base. So 1.25 plus 2. So that's 3.25. For the next one, I'm going to use this base which happens to be the base of the one previous, and then this base right here. So that's 2 plus 3.25, so that's 5.25. And then for the last one, I'm going to use this base right here, which is the one from the previous, and the last base. So that's 3.25 plus 5. So that's, doesn't fit, 8.25. All right, so let's see, 1/2 times 0.5, or 1/2 times 1/2, that's 1/4. And then 2.25 plus 3.25 plus 5.25 plus 8.25, that's 19. So my answer is 19 over 4, or if you really must, 4.75. Now notice, if you paid attention, I had to use this base twice, I had to use this base twice, and I had to use this base twice. Well, that's the more formal definition for trapezoidal approximation. And if you would please write this somewhere. So what they do is they simply just go ahead and tell you, okay, the height divided by 2, and then your first y value, your initial y value, the first one, y naught, that's what it's called. Yes, naught. So y naught plus 2 times your second y value, but they're going to call it y1. Yes, just get over the fact that it's y1. So this is y naught, and this is y1. And then plus 2 times your next y value. And then you continue this way. You multiply by 2 every single y value until you get to your last one. Okay, the second to the last one should be, so 2y, right? 2 times that y, which we're going to call n minus 1, because n is going to be the last one. And then plus just y, and then this is the last one. Okay? The last y does not get multiplied by 2, nor does the first y. And this is the more formal. They also, what they do is, they consider the height to be b minus a over n. So your interval divided up into n trapezoids, that's your height. And of course that only works if you're actually using equal subintervals. Okay, so example 2. The trapezoidal approximation of sin x from 0 to pi dx using 4 equal subdivisions of the subinterval of integration is... Okay, so, well, first off, let's do a little bit of graphing. Remember, sine looks like this. Okay, a little better than that. But it kind of looks like that. So here is 0, and here is pi. And then here is pi over 2. And then here is pi over 4. And here's 3 pi over 4. They want us to divide this up into 4. So I'm going to have 0, pi over 4, pi over 2, and pi. Oops. Okay. And then this will be my y value, whatever. So I'm going to plug in 0 to sin x, and I get 0. I plug in pi over 4, and I get the square root of 2 over 2. I plug in pi over 2, and I get 1. I plug in pi, and I get the square root, or sorry, I said that backwards. So sorry. Well, not backwards, but whatever. I plug in pi over 2, and that's 1, and then pi is 0. Okay, so I have my heights. I know that I need 4 of them, 4 trapezoids. My heights slash width, right, is basically how wide these subintervals are. And this from 0 to pi over 4 is just pi over 4. So this is going to be my width, which is pi over 4, divided by 2, but I don't want to write a fraction inside of fraction, so I'm just going to leave the 1/2 there. There's my 1/2. And then I'm going to figure out my bases. So you add the first one once. You add the second one twice. So 2 times the square root of 2 over 2. The next one goes twice as well. 2 times 1. And then the last one is just once. And then I get, so pi over 4 times 1/2. And I know I can simplify that as pi over 1 or pi over 8. But this is multiple choice. And notice how none of these are pi over 8. So let me not get ahead of myself. And then, let's see, 2 square roots of 2 divided by 2. So these 2's cancel out. And what I have is the square root of 2 plus 2. Right, we see that? Now again, if I look at my answers, I have a 2 plus square root of 2, but then pi over 4, where's the 1/2? So no. I don't have anything else that looks like 2 square root of 2, 2 plus square root of 2. So let's see, the 1/2. I'm going to go ahead and divide these by 2. Right? Same thing. So pi over 4 is the square root of 2 divided by 2 plus 2, which is 1, sorry. Which is 1. And then you must be thinking, well, hold on. This is still not the same. And that's because I'm a dodo head and I forgot something. I'm sorry, and I'm not recording this. I mean, I am recording this, so I'm not going to redo it. Hold on a second. I missed something. If you caught it, congratulations, you're awesome. I did 0, which is right here. I did pi over 4, which is right here. I did pi over 2, which is right here. I totally skipped 3 pi over 4. 3 pi over 4. And then the last one, of course, is pi. My bad. At 3 pi over 4, the answer is square root of 2 over 2. And then at pi, my y value is 0. So this is the little sucker I'm forgetting right here. So that does change this a little bit. Just a little bit. So let me go ahead and redo this part. And this part. Okay. So what I should have done was 2 times the square root of 2. Oh, the 1 could have stayed. Plus 2. Plus, and then here's the thing. I needed to do square root of 2 twice. And then plus 0. So that's what the purple stuff is the stuff I'm fixing. I'm sorry. And now this would make better sense. So I have the same situation going on here that the 2's cancel out. So I have 2, and then I have a square root of 2 right here, plus another one. So that just still makes it plus 2 square roots of 2. And then the 1/2, I guess I kind of erased it. But see this 1/2 right here? Like I said before, it's not in any of my multiple choice answers. So let me get rid of it by dividing that by 1/2. Or dividing by, sorry, multiplying by 1/2 or dividing by 2. So 2 over 2, that's 1. And then basically these cancel out, right? So it becomes 1 and then becomes just the square root of 2. And then looking at my multiple choice whatever, the only one that looks like this, oh, I mean, okay, if I look at this and I look at that, you know, those are my options. But then the pi over 4 is what I needed, so it's C. Sorry. Okay, example 3. Suppose the table below shows the velocity of a model train engine moving along a track for 10 seconds. Using a trapezoidal approximation with 10 subintervals, estimate the distance traveled by the engine in the first 10 seconds. Okay, so for trap, it's going to be h divided by 2. So my widths are all 1. So 1 divided by 2, or 1/2 basically. And then the first one and the last one do not get doubled. Oh, look, they're zeros. So that works out perfectly. And then so 2 times 12, that's 24. Plus 2 times 22, that's 44. Plus 2 times 10, that's 20. All I'm doing is I'm multiplying all of these by 2 and adding them up. So 2 times 5, that's 10. 2 times 13, that's 26. 2 times, where am I? 11 is 22. 2 times 6 is 12. 2 times 2 is 4. And then another 2 times 6, that's another 12. And then 0. I don't have to add 0, right, folks? So 1/2. And in here, I did the math previously. I got 174. And so 87. So the train, is it a train? The train traveled 87 inches. Okay. Example 4. So this is one of those logical thinking questions. The function f, oh no, not this one, it's the next one. Sorry. The function f is continuous on the closed interval from 1 to 7 and has values that are given in the table above. Using the subintervals 1, 4, 4, 6, and 6, 7, what is a trapezoidal approximation of, and then f of x from 1 to 7. So basically, they're asking you to find the area using trapezoidal approximation for the interval from 1 to 7, but all they gave you was a table of graphs, or a table of values. And they want you to split it up from 1 to 4, that's going to be one trapezoid. So basically what we have here, so from 1 to 4, from 1 to 4, they want you to do one trapezoid. And then, I'll 1, 4, 6, and 7. From 4 to 6, they want you to make another trapezoid. Okay, and I'm getting these from here, people. Okay, I'm not making this up. And from 6 to 7, they want you to make another trapezoid. Okay, so see how my intervals are not all the same? So I'm going to have different heights for these. So I can't just use one H. No, no bueno, it's not going to work. So for my first one, my width, I'll do it in red. My width is 3. So that's going to be 3 divided by 2. And then I'm going to take my base 1, which is 1. Or sorry, which is whatever I get when I plug in 1, which is 10. And whatever base 2 is whatever I get when I plug in 4, which is the 30. So what I like doing on my paper is I'm just like, okay, it's these two. So 10 plus 30. That takes care of my first trapezoid. Now I'm going to add that to whatever I get for my second trapezoid. For my second trapezoid, the width is 2. So it's 2 divided by 2. And then my base 1 is whatever I get when I plug in the 4. And my base 2 is whatever I get when I plug in the 6. So it's these two. So 30 plus 40, or 70, right? And then for the last trapezoid, notice I had to do this differently because the intervals are not the same. Okay, these are not all the same size trapezoid. Or same, sorry, height or width, however you want to call it. And the last one has just a width of 1. So it's 1/2, right? 1 divided by 2. And then it's these two numbers. 40 plus 20. Okay, and that's how you would find this one. So let's see. This is 40, this is 70, and this is 60. So 40 times 3, that's 120 divided by 2, so this is 60. Plus 70 times 1, because 2 over 2 is 1. And then 1/2 times 60 is 30. So my answer is 160. All right. Last one. Using 8 equal subdivisions of the interval from 2 to 12, the LRAM approximation of f of x from 2 to 12 dx is 16.6. And the trapezoidal approximation is 16.4. What is the RRAM approximation? Okay, so remember, earlier I told you that this is equal to this. This is algebra, folks. LRAM is 16.6. So, substitution property, 16.6 plus LRAM is what we do not know, and equals trapezoidal approximation is 16.4. Substitute that in. Algebra. Solve it. Let's see. I want to get rid of that pesky 2. So I'm going to multiply this by 2 to get rid of it. Whatever I do to one side, I must do to the other. So this is 32.8 equals 16.6 plus LRAM. If I want to find LRAM, I would get rid of that 16.6 by subtracting it. And LRAM is 16.2. And there you go. All right. We have a quiz next class. Yes, tomorrow we have another quiz. I will be giving you back the quiz you took on Friday. And we have a test on the 12th. Please complete your Chapter 5 review.